Welcome to this lecture series in complex numbers. In this lecture, we'll look at a problem that appeared in IMO 1986. It's the second problem in that exam. And let me describe the problem. So, fix 3 points A, B, C in the plane. So, 3 distinct points are shown here. And a man starts at a certain point P0, which is shown here, and walks directly to A. And then what does he do? He turns by 60 degree, and so if you draw this dotted line and let's say this is the 60-degree angle, then he walks in this direction so that these two things are equal. So he reaches to a point P1 such that this distance is same as that distance. All right, and then from here he will walk directly to B, then again turn by 60 degrees, this is 60, and reach a point P2. And then he'll walk directly to C, again change his direction by 60-degree anti-clockwise, such that this distance is same as that distance, and will reach to a point P3. And then again he will walk directly to A, turn by 60 degrees, so that P4A and P3A are the same distance apart, and he continues to do this dance. All right, so let me expose the hidden things. So at A, he turns his direction by 60 degrees. As I said, he reaches A, then turns his direction by 60-degree anti-clockwise, and walks to a point P1 such that this distance P0A is equal to P1A. And then from that, he performs the same thing 1986 times, successively. First he pivots around A, then pivots around B, then pivots around C, as I described. So once more, he starts at a point P0, walks towards A, changes his direction by 60-degree anti-clockwise, and reaches a point P1 such that P0A is P1A. Then he does the same thing with B, reaches to a point P2 such that P2B is P1B. Then he does that with C. Then he does that again with A. Then he does that with B. Then with C again, and so this way he will do this 1986 times, right? First time A, second time B, third time C, then A, then B, then C. So he does this 1986 times successively, and he discovers that at the end of this 1986 steps, he reaches back to his starting point P0. All right, and what we want to show is that that ABC form the vertices of an equilateral triangle. Right, so that is the problem, that if he reaches back to his starting position after this whole nonsensical thing that he's doing, we want to show that ABC form the vertices of an equilateral triangle. So it seems like a daunting problem at first, but it is actually very, very simple. You can solve it in various ways. In this particular lecture, we'll look at it from the lens of complex numbers, but you can solve it with even plane geometry or linear algebra. There are other ways to do it. Essentially, at the heart of the matter, the same thing is working, but I think the neatest solution comes from complex numbers. All right, so as usual, you are encouraged to pause the video and attempt the problem yourself, and then only look at what is the solution that I'm describing. All right, so here is the thing. So first we have some notation. So let A1, A2, A3, A4, A5, A6, and so on up to 1986 be the sequence A, B, C, A, B, C, so on, ending at C. So basically all we have done is we have defined A1 as A, A2 as B, A3 as C, then A4 as A, A5 as B, A6 as C, and then A7 as A, and so on, and you'll see that A1986 will be assigned C. Okay, so just some notation. Also, let alpha be this complex number, cos pi by 3 plus iota sine pi by 3. So it is basically, if this is the complex plane, then you take the unit segment which is inclined at an angle 60 degree. All right, so with these notations, let us describe what is P1. So let P not be the origin. So we may assume that he starts at the origin. P not be the origin of the complex plane. Origin, by origin we just mean the zero of the complex plane. So let us find out what is P1. So this is, let's say this is A. He starts at, suppose this is P naught. In my previous figure, P naught was somewhere else, but let's say this is P naught. So he walks towards A and then turns by 60 degree and reaches P1. So what I want to do is express P1 in terms of A1 and P naught. A is equal to A1, so I might very well write A1 here. So what I want to do is express P1 in terms of these two things. So what is P1? P1 is this vector added to the point, to the complex number A1. So this vector is nothing but P1 minus A1. But what is this vector? This vector is nothing but this vector rotated by 60 degrees. So what is this vector? This vector is A1 minus P0 rotated by 60 degrees, and then add that to A1. Right? So what is this guy? This guy is that vector, because it is just the rotation of this guy, which is that, by 60 degrees, and hence you get that vector. That's the definition. That's how the problem is defined. And you add that to A1, because when you add this vector to A1, you get P1. So this can be written in a different way. This is equal to, or maybe I'll write it here. This is equal to 1 plus alpha A1 minus alpha P naught, right? So this is just a computation. So basically P1 is, let me rewrite that. So P1 is this. And if you compute P2, will come out to be, by the exact same logic, this P3 will come out to be that. And so on. Maybe one more. And so on up to 1986. All right. So let us maybe, what we will do is we will express P1986 purely in terms of these AIs. So to get there, I mean, one can get there directly, but let's see what is P2. So what we will do is we will eliminate P1 from this equation, because we already know the expression for P1. So if we do that, what is this? This is equal to, I hope I don't run out of space. This is 1 plus alpha A2 minus alpha times 1 plus alpha A1 minus something, but I don't care about that something, because this is 0. P0 was the origin, so this term is really 0. So let me erase that, because otherwise unnecessarily confusion will be caused. So that is what this expression is, right? So another way to write this is just take 1 plus alpha common. And inside we have A2 minus alpha A1. So we have the expression for P2. It's not so horrible. Now let us compute P3, because all we need to do is substitute the expression for P2, and that will turn out to be 1 plus alpha A3 minus alpha times the expression that we just computed, 1 plus alpha A2 minus alpha A1. And what does it become? If we compute it, it is 1 plus alpha A3 minus alpha A2 plus alpha squared A1. I hope this is correct. No, I don't think there is any problem with it. Yeah. So that's what it is. And if you just keep going, you can detect a pattern here. So PK, or let me just directly write P1986. P1986 will turn out to be, let's say K is equal to 1986. So PK would then be 1 plus alpha AK minus alpha AK minus 1 plus alpha squared AK minus 2 minus alpha cube AK minus 3, and so on. So the signs will alternately become minus, plus, minus, plus, and the exponents will increase. So here alpha to the power 0, then alpha to the power 1, alpha squared, and so on. So this will go up to wherever it will go up to. So that's what it is. And this is nothing but, what is this? This is C. This is B. This is A. This is C, B, A. So this is equal to 1 plus alpha C minus alpha B plus alpha squared A minus alpha cube C plus alpha to the power 4 B minus alpha to the 5 A and dot dot dot. That's what it is. But here is the point. What is minus alpha cube? Minus alpha cube is 1. Just compute, or you can see it geometrically. So if this is alpha, what is alpha cube? Alpha cube is minus 1. And if you again multiply with the minus 1, you get 1. So minus alpha cube is 1. And then, similarly, basically all the coefficients of C you will see are equal to 1. And how many times, therefore, C appears here? 1986 divided by 3 times. So this is 1986 divided by 3C. Then once again, same thing for B. Here you have minus alpha, and this is also equal to minus alpha. Right? Alpha to the 4 is same as minus alpha. So all the coefficients of B that we see here are the same, and they are same as minus alpha. So what we will get is 1986 by 3 alpha B. And in case of A, everything will be alpha square. This is alpha square, but this is also alpha square. So we get 1986 by 3 alpha squared A. So that's what that is. And this is equal to pk, which is p 1986. But that is given to be equal to 0, meaning it was given that the man returns to the original position. The original position was p0. P0 was origin as we chose it. So this is 0, and therefore what we get is 0 is equal to 1 plus alpha 1986 by 3 c minus alpha b plus a, which implies 0 is equal to c minus alpha b plus a. Right? Sorry, not plus a. This is alpha squared a. Sorry, my mistake. This is alpha squared a. I missed a term. Yeah, this was alpha square. I miswrote it. So we have that. And now you can easily show that it is an equilateral triangle. Here is the argument. Sorry, this bracket is gone. So what you do is you have minus a equals, okay, so let me write it this way. So this is alpha b minus alpha squared a equals c. All right, which implies alpha b minus alpha square a minus a equals c minus a, which is alpha b minus 1 plus alpha square a equals c minus a. But what is 1 plus alpha square? 1 plus alpha square is equal to alpha, right? Because here we have alpha, this is alpha squared. If you add alpha square and 1, you get alpha back. You can compute it. This is just a matter of computation that you can check this. So this is equal to alpha, and therefore what we get is alpha b minus alpha a is equal to c minus a, which implies alpha b minus a is equal to c minus a. And therefore, if suppose this is our triangle, yeah, this is b, this is a, or maybe that is b. I think it will come out to be this way. So b minus a is that vector, and c minus a is that vector. So if you rotate this vector by 60 degrees, so I think it will be the other way around. It will be a c b. Let's see. Yeah. So b minus a is that vector, and c minus a is that vector. And what we are given is that if you rotate b minus a by 60 degrees, you get c minus a. So the magnitude of b minus a and c minus a are the same, because if you take modulus both sides, you get on the left side modulus of b minus a, and here modulus of c minus a. So at the very least, you have an isosceles triangle, but the angle between the two segments is 60 degrees is what this is saying. Maybe this figure is a little bit wrong, because b minus a is that vector. If I rotate this by 60 degrees, then it's a little bit of a problem. If I take this, then also it's a problem. alpha times b minus a. B minus a is this guy. Yeah, this is correct. So this is how the picture is going to look like. So if you just decode this thing, the picture is going to look like this. Once again, b minus a is that vector. If you rotate that by 60 degrees, you get that vector, and therefore the triangle has to be equilateral because these two things are equal and this angle is 60 degrees. That's it. So very nice solution to a fairly difficult looking problem, although as we saw, it is more or less a matter of computation. All right, so with this, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.